In this video, I want to formally introduce velocity. Velocity is defined as the change in position over the change in time. Remember, this triangle symbol means delta, which is a Greek letter, and it stands for change. The reason I chose X in this case is just for convenience. This could have been any letter that represents change in position. So for example, it could have been delta D, for example, but we can consider just along one axis in this case. Remember, our displacement vector would be the hypotenuse of a right triangle if we have a component in the x and y direction. So I can basically just consider one dimension when I'm thinking of the change in position. Remember, displacement means the shortest distance between 2 points, your starting point and your end point. So it doesn't matter, for example, if I took some curvy path to get from the beginning to the end. What matters is the shortest distance between those 2 points, which is in fact a straight line. So for that, I can then choose to use just a one-dimensional x-axis. So we see then that velocity again is the change in position with respect to time. So I may have started here at some, say, x equals 0 position, and I came over here then and ended up at, say, x equals 10. And if that took me 2 seconds, then in this case, my velocity would be v equals 10, let's say meters in this case, in 2 seconds. So let's call these meters. And then I can simplify this fraction and then see that my velocity was actually 5 meters per second. Again, this was for the case of displacement of 10 meters in 2 seconds. The 2 seconds is the delta t, that's the change in time. So if time started obviously at 0 seconds and then went to 2 seconds, the delta t is 2 seconds. So hopefully that makes sense to you. That is the formal definition of velocity, is the change in position over the change in time. So when we say something like miles per hour, that's another valid form of velocity if it has a direction. It's just considering it in the form of miles per hour. So meters per second is in fact the unit of velocity that we'll use in our physics class. So again, meters per second is the standard unit of velocity. So one other thing I want to look at is the velocity versus time graph. In this case, it's going to be pretty simple, but we're also going to be using the velocity versus time graph for acceleration. So we need to become familiar with it. In this case, we have constant velocity. Now this is a different velocity. This is 4 meters per second. So this would be 4 meters per second. Notice that is the height of this graph, or you can think of it as the y value. The height is 4 meters per second, and that is the velocity. And then on what we would consider as the x-axis here, I have time. And we can see that we have traveled 4 meters per second for 10 seconds. So the reason I want to look at this is because if you multiply the velocity times the time, you're going to get a distance. And it's actually considered the area under this curve. Why is it the area of a curve under this curve? Well, think of the area of a rectangle. It's just the base times the height. The height in this case is 4 meters per second. The base is 10 seconds. So what do we get for the area when we multiply those two values together? So let's write that out over here. So we're interested in the area under the velocity versus time graph that we have. So our height is 4 meters per second. And I'm going to draw a line just to distinguish between the first example and this other example because they're different velocities. So the height of this rectangle is 4 meters per second. And the width is 10 seconds. And again, this is a rectangle, so to find the area, we multiply the height times the width. So that is area of rectangle is going to be equal to 4 meters per second, the height, times the width of 10 seconds. Now we see here we have a seconds in the denominator and a seconds in the numerator. So we are left with 40 meters. And that's pretty cool. So if you travel for 4 meters per second for 10 seconds, you will travel 40 meters. And you might say, well, that's pretty simple. I mean, it's just a rectangle on the graph. But what we're going to see is when we introduce acceleration, acceleration is changing velocity. So here we can see the velocity stayed constant at 4 meters per second during the entire 10 seconds. If we introduce acceleration, well, then velocity is not going to be constant, meaning it'll be changing from a value. Say, for example, like this straight line. It would start at 4 meters per second and it ends up here around 8 meters per second. That's with the introduction of acceleration. So for this case, I wanted to introduce the velocity versus time graph so we could see how this area under the curve is in fact the displacement when you're traveling a certain velocity. The last thing that we need to note then is that velocity is in fact a vector. So in this example, I've just been discussing one dimension along this x-axis, but velocity can be in 2 dimensions. So for example, we could have a 2D velocity vector along some x and y axis that's pointing off at some angle, just like with displacement. So this could be velocity vector and it would have some angle with respect to the x-axis. So while I didn't note it formally up here, since we were just talking about one dimension, velocity is in fact a vector. So a velocity could be, for example, if theta here equals 45 degrees, we could say this velocity, magnitude of this velocity is, say, 5 meters per second. And the total vector then would be v vector equals 5 meters per second at 45 degrees north of east. Again, this is just one example. With this angle, 45 degrees, velocity can point in any direction, so it is in fact a vector. It needs to have both a magnitude and a direction.